to 3, we must choose. I don't really know what that part of the sentence is trying to say. So we'll just skip that. So what we need to do is we need to start with this expression. In absolute values, I've got 2x plus 1 minus 7. Now again, what this is saying is the distance between 2x plus 1 and 7. Remember, we wanted that to be less than 0.01. And so the second part was to figure out how close x had to be to 3. So in other words, the distance between x and 3 has to be how small. So we're going to say that the absolute value of x minus 3 is less than some unknown quantity. And this unknown quantity is the delta. This is epsilon, and that's delta. Alright, so here's what's going on. This is actually very much what we did before, it's just written in a different way. So we're starting out with the distance between f of x and 7 being less than 0.01. I simplified what was inside the absolute value, so it becomes 2x minus 6. Now there's a common factor of 2 here, so let's take that out, and that gives us the absolute value of 2 times the quantity x minus 3 is less than 0.01. Now the absolute value of a times b is equal to the absolute value of a times the absolute value of b. Let me write that down. The absolute value of a times b is equal to the absolute value of a times the absolute value of b. So we can split this apart into the absolute value of 2 times the absolute value of x minus 3 is less than 0.01. And again, the absolute value of 2 is 2. We divide each side by 2, and we get that the absolute value of x minus 3 is less than 0.005. Remember what this says. The distance between x and 3 has got to be less than 0.05, and that's what we found before. Alright, so again, the idea is that no matter what someone chooses for this number, we should be able to find this number. Well, we don't want to do that for each and every epsilon that someone gives us. It would be impossible. So we need to come up with a shorter way that handles all values of epsilon at one time. And that's getting us closer to the rigorous definition of limit. Alright, so let's go back again to the non-rigorous definition of limit. What we're going to do is we're going to take this and rewrite it in terms of absolute values. And so the first part is okay. But when it gets down here, so that to the part where we say that f of x can be made arbitrarily close to L, here's what's going to happen. Okay, so this phrase, there is a number L such that f of x can be made arbitrarily close to L, can be rewritten this way. There is a number L so that the distance between f of x and L can be made arbitrarily small, right? If f of x is close to L, that means the distance between those two numbers is small. So there is a number L so that the distance between f of x and L can be made arbitrarily small. Well, and this is the part where we introduce the absolute values. So we can rewrite that as there's a number L so that the absolute value of f of x minus L can be made arbitrarily small. But again, what does this arbitrarily small mean? It means smaller than any arbitrary positive number epsilon. So if someone gives us an epsilon like 0.01, well, that's one value of epsilon, but it's arbitrary, it's not stated, it's not specified. So we are just going to go with representing this value as this lowercase epsilon. So what that's going to get us down to then is that phrase that we've been talking about is now going to be, there is a number L such that the absolute value of f of x minus L is less than epsilon for any positive, arbitrary positive number epsilon. So f of x and L can be made arbitrarily close together. Alright? Now the other phrase we need to concentrate on is this part down here, x is close to c. Well, just like before, what we're going to rewrite that, or in terms of the distance. We're going to think of this as the distance between x and c is small. And again, what does it mean to be small? Well, in this case, small means smaller than some positive number delta, so we'll write that part of the definition as the absolute value of x minus c is less than delta. Now, there's one other thing that we have to take care of. Remember that we said that we didn't want x to go all the way to c, so how can we take care of that? Well, what happens if x goes all the way to c? What happens if x equals c? Then this distance, if x minus c if x and c are 0, if x and c are the same, then x minus c is 0. So we don't want that distance to be equal to 0. So we also add in this part. We want that distance between x and c to be positive, greater than 0. So that's how we get this inequality. 0 is less than, the absolute value of x minus c is less than delta. Putting this all back together, we get the rigorous definition of limit. Here's our definition. Let f be a function that is defined on some open interval containing c, except possibly at c itself. If there is number L such that for every positive number epsilon there is a positive number delta, so that the absolute value of f of x minus L is less than epsilon whenever 0 is less than the absolute value of x minus c is less than delta, then we will say that the limit of f of x as x approaches c is L. So again, what this is saying is the distance between f of x and L can be made small. How small? Well, as small as anybody wants. Arbitrarily small. By making certain that the distance between x and c is sufficiently small. In other words, less than delta. But not 0.